the first of the series of my lectures, and as Christian already mentioned, my lecture will be more experimental view on liquid crystals, topology of liquid crystals, surfaces, fields, and an interplay of topological defects in optics as well as matter, in particular soft matter, liquid crystals. And so we all know that topology plays an important role in many branches of science, right? So in here you can see a preview of some of the examples. It's definitely by far not an exhaustive overview of important roles that topology plays in different branches of physics, but you can see here examples from high energy physics, optics, atomic molecular optical physics, cosmology, hard condensed matter physics, and of course today we'll talk a lot about examples from soft condensed matter and optics too. Right, so in all of those examples you can see in here, topology really defines behavior of those physical systems. And at the same time, it also makes this behavior fairly universal for very different physical systems. And so one example that I would like to give in here that would show how topology makes different phenomena and behavior in very different physical systems look somewhat similar is by comparing the topological defects in cosmology, which are cosmic strings, and liquid crystal defects, right? So quite some time ago, Tom Keeble developed the theory of cosmic strings, the defect lines that played an important role in the early universe cosmology. And a little bit later, another famous physicist who is coming actually from South Africa proposed testing some of those ideas using topological defects in liquid crystals, and Mark Bowick, who is here with us in the audience, also contributed greatly to the development of those ideas. And so those science papers that you can see cited in here did actually demonstrate that there is one of which is co-authored by Neil Turok and the other one by Mark Bowick here. Those papers demonstrated that indeed the behavior of topological defects, the dynamics of topological defects are similar in those two very different systems. And liquid crystal defects at the transition from disordered isotropic phase to ordered nematic liquid crystal phase can be used as a test bed to test the theories in cosmology. And so later on this resulted in a lot of follow-up research in condensed matter physics in particular, because the different condensed matter systems could be used to test ideas from cosmology, and you can see how the developments in topological defect understanding in cosmology enriched the understanding of defects in condensed matter physics, and vice versa, right? Because it wouldn't be that easy to test what really was happening with cosmic strings, right? You cannot replay the early universe, but you can easily melt liquid crystal, go into isotropic phase in a laboratory, cooling down to nematic phase, and probe the dynamics of topological defects in liquid crystals. Right? So you can see that one advantage that we have playing with defects in soft condensed matter systems is that we can do experiments, right? We can test ideas, and some of those ideas are not constrained to self-condensed matter physics systems. They can have universal importance. They can make an impact on our understanding of cosmological phenomena as well, as you can see from this example. And so in a series of my talks, I will first today introduce some key concepts and experimental techniques that allow us to probe topological defects in self-condensed matter systems. First, this is what I'll attempt to do today. Then we will discuss topologically non-trivial field configurations in liquid crystals, and actually as I'll be introducing those techniques, I'll motivate why is it important to have the access to those techniques through some particular examples of topological non-trivial field configurations. Then we will see that we can use light and optical vortices, defects in laser beams of light, to control topological defects in matter and liquid crystals in particular. Then I'll demonstrate that we can also do opposite. We can use defects in matter, in liquid crystals, to control topological defects in light, the vortices and laser beams. Finally, I'll also demonstrate that we can use colloids, tiny particles that undergo Brownian motion when dispersed in different fluid hosts. In our case, those fluid hosts will be liquid crystals, and we will see that there is very interesting interplay between topology of surfaces of colloidal particles and field configurations that you induce by colloidal inclusions in liquid crystals, and we will see how those colloidal particles can be used to generate on demand different types of field configurations and defects in liquid crystals. All right, so from very nice introduction by Jonathan that you just had, you already know about liquid crystals. You know that you can describe this orientational ordering by a director, right? And you also know that liquid crystals stand in between solid crystals and isotropic fluids, having properties of both mixed in a very unique way, right? And this provides us with lots of advantages, both in doing fundamental science with those systems and in using them in many practical applications, right? So mostly Jonathan's talk was focused on nematic liquid crystals, but we can also have chiral nematic liquid crystals when we have molecules that lack mirror symmetry, right? So in here you can see two different molecules. One is the 5CB, the pentyl cyanobiphenols that Jonathan was discussing with you in the previous lecture. We can also have very similar molecules that could have so-called chiral center, as you can see here in the hydrocarbon tail of this molecule. The presence of the center breaks the mirror symmetry, so that rather than forming nematic-like phase when all the molecules align nicely parallel or on average roughly parallel to each other, right? In this chiral phase, they will want to twist around the axis, which we call helical axis in here. And the distance over which they twist by 360 degrees is called cholesteric pitch, right? So locally, when you zoom into a tiny region, they look very much like nematic liquid crystal. You barely would see difference, right? But as you go to larger scale, you will notice this twisting of the director, right? And so the cholesteric pitch can range in values from roughly 100 nanometers or so in chiral nematics, or cholesterics, that's the other name for this liquid crystal phase, to hundreds of micrometers or infinity. When it's infinity, it's nothing else but nematic liquid crystal. Right? And so now we will, in my talk, in my series of talks later on, we will see a lot of interesting behavior and topological defects in cholestatic liquid crystals or chiral nematic liquid crystals. Now, I know that we will also have some talks on blue phases later on during the summer school, and those are also formed by molecules that lack mirror symmetry, chiral molecules, but in here the twisting occurs not only along the helical axis, right? So it's not one-dimensional twisting, but we typically define the so-called double twist cylinder, where you can imagine the molecules being parallel to the cylinder axis in the very center of it, but they would twist as you would go away toward the periphery in all radial directions, just like depicted in here, right? And so now you can form from those double twist cylinders different types of cubic lattices, right? And those this is the organization of the so-called blue phases, cholestatic blue phases. The lattice parameter in here is typically comparable to wavelengths of light in the visible part of optical spectrum, and in the first materials in which those phases were discovered, this selective reflection that results because of this fact that light wavelengths is comparable to periodicity and we have Bragg reflection. So that was observed first for blue light, and that's where the name comes from, right? Cholestatic blue phases. But in fact, we can have other colors reflected from those cholestatic blue phases as well. Depending on the material, you can see here different monocrystals oriented differently with respect to the viewing direction and giving different selective reflection colors. The reason I am introducing those cholestatic blue phases is also because we will see later on that very often we have formation of those double twist cylinders in the liquid crystal systems, and they give rise to very interesting behavior and formation of topological defects. Right, so I'm sure you're familiar with many practical applications of liquid crystals. The most common ones are depicted in here, but this is by far not, again, exhaustive representation of where we see the applications, right? Displays of large areas, TVs, different cell phones, laptops. I'm sure many of you have devices in your pockets that utilize liquid crystals, but I would like to ask this question, quicker question: what do you think will be future applications of liquid crystal technology? This is before we go to discuss very fundamental topological aspects. Let us just take a minute or so break and think what will be the practical applications of the future.
It only goes up to E.
That's right.
No F.
It's a trick question.
Okay, so can it be all of the above?
We vote by touching our noses for F. Okay.
Yeah, we have, sorry.
Need a picture. I lift mine up here.
I just don't have one. I don't have one.
Okay, so don't think too hard. There is no correct answer here, but I'm just curious what you think. Okay, let's stop the system. And this is distribution we get. So interestingly enough, the most popular answer is D, which is assembly of microstructures. Good. So let us now focus on more fundamental aspects. And before we do this, I would like to give a little overview of topology. And so we know that as physicists, we are always assuming spheres, right? There is this famous spherical curve assumption that we very commonly make. Well, so in topology, it's even more so, right? There is no difference as long as you can morph things one to the other with the same topology. And so the surfaces that can be morphed to each other are called homomorphic, or in other words, non-distinguishable. So if you would take an apple and some other complicated surface that still can be morphed into a sphere, it's homomorphic to sphere. Now, the same can be done with other surfaces, right? So for example, a coffee mug is homomorphic to donut and to a torus surface in here, but a sphere cannot be smoothly morphed to a torus, as you can see, because the other one has would have to be cut to be morphed to spherical surface, or vice versa. Right? So those are then topologically distinct from each other. And this is perhaps what everybody knows about topology, right? The properties of such surfaces, and those properties stem from the Poincare theorem, which says that every closed, simply connected surfaces without holes is homomorphic to sphere. We can see that this is not the case for a torus surface. The two surfaces in here are topologically distinct from each other. Now, it turns out that we can extend this Poincare theorem from the three-dimensional world in which it was originally introduced for two-dimensional surfaces to higher dimensions, right, where we can have surfaces, three-dimensional, four-dimensional surfaces, and so on. But historically, it turned out to be not so easy to prove that Poincare theorem, which in higher dimensions would be Poincare conjecture originally, would still work, right? So Poincare, in his original paper back some over 100 years ago, was saying, well, it would be interesting to know whether, this statement that he made about the two-dimensional surfaces would also work in high dimensions, right? And so, so is it that sphere in high dimensions is still the simplest connected surface or not? Was not so easy to prove, and first it was proved for 6 and high dimensions in 60s, resulted in Fields Medal, and as you probably know, this is the highest honor for scientific achievement for mathematicians. Right, then a little bit later, was proved for the four-dimensional surfaces in 5 dimensions, and again resulted in Fields-Mendel. But when it comes to the 3-dimensional surface in 4-dimensional space, right, which is just adding 1 degree of freedom to the 3-dimensional space in which we see things, it turned out to be very difficult. Right, so it was this Poincare conjecture for 3-dimensional surfaces in 4D was eventually proved in 2003 by Grigori Perelman, and it was called Scientific Breakthrough of the Year. He was awarded the Fields Medal in 2006, and because this problem of Poincare conjecture was so long-lasting and difficult to be proved for quite some period of time, this problem was selected to be one of the Millennium Prize problems, and it's the only one that so far was solved. So he was also given the Millennium Prize, which is $1 million, but declined to accept all of those awards and also the $1 million as well. So my question to you is, why? Yeah?
He was too shy.
That could be the case, but think as a topologist. More ideas? Well, we can only speculate, but if you think about this 1 million, it's topological equivalence to, well, apples and donuts, right? If you think in terms of topology, it's not that much. Okay, so let us talk a little bit more about spheres. So we are very familiar with the two-dimensional spherical surface in 3 dimensions, right? We know that we can describe it by this simple equation. It's nothing else but a set of points equidistant from the point of origin in here, right? We can describe it by this equation. And we know also that in 2 dimensions, S1 sphere is nothing else but a circle, right? So again, it's a set of points equidistant from the center of origin in here. Now, if we go to higher dimensions, it's a little bit hard to draw or even imagine what that surface would look like, but we know that mathematically we can describe it very easily, right? We would have just one another coordinate axis, and the equation would be just a simple extension of the equation that we are very much familiar with for 3-dimensional space. But the question is, can we see, can we understand or describe those types of spheres? Well, so imagine we would be living in a 2-dimensional world, right? And then we would have an S2 sphere, 2-dimensional spherical surface in 3-dimensional space. In order to characterize it, to describe it, what we could do is to use what we know as the stereographic projection, right? So we could project all points on that spherical surface to the 2-dimensional plane, and all of those points could be uniquely represented through the means of this stereographic projection on this two-dimensional plane, so then we could understand them, right? Because we would be living in two-dimensional world of this plane. This idea can be extended also to high-dimensional surfaces, where we again could use stereographic projection to describe those surfaces in three-dimensional space in which we can see and understand things, right? So this S3 sphere could be characterized by means of stereographic projection, and we could again project certain circles on that S3 sphere by projecting to the three-dimensional space, and then also characterizing those circles as points on the S2 sphere. Additionally, we could characterize the S3. Now, what's interesting to note in here is that as we would be projecting the circles from S3 to the three-dimensional space, they would be linked with respect to each other, right? And this makes them already topologically non-trivial. This is nothing else but the so-called Hopf fibration, which allows to present S3 in terms of S1, right, the circles projected to 3D space, and also additional points on S2 sphere. So as I already mentioned, it's topologically not trivial, and there is very beautiful geometry in here because all of those circles are linked with respect to each other, and you can define the tori on which those circles would be on the tori surfaces on which you can draw those circles. And so, as I already mentioned, they are linked with respect to each other. And so this Hopf fibration allows us to understand and represent the high-dimensional spherical surfaces by means of such representation. Obviously, it became part of many physical and mathematical theory because it's something so general, telling us about spherical surfaces in high dimensions, and this S3 in particular. But the question is, can we see it in experiments? Right? So the four-dimensional space is not accessible to us, right? But the reason I'm showing here Paul Ackerman, who is with us in the audience, is because he was able to experimentally see the director field configuration in liquid crystals that is homeomorphic with the Hopf fibration depicted in here, that, as we already know, is representing S3 or stereographic projection of it. Right, so I'll now introduce a series of experimental techniques that will allow us to understand how we can understand the topological defects and topological non-trivial field configurations in liquid crystals, and how we can demonstrate that, for example, a certain structure that we will observe will have certain topological features, and in particular, in here you can see the so-called Poincare construction of the Hopf vibration of director fields in liquid crystal done by means of computer simulations, and then also reconstructed from experiments where the different colors represent orientations of liquid crystal director and liquid crystal molecules. As we already learned, average orientation locally, molecules such as 5Cb. So we already know that this is obtained in liquid crystal, right? The main goal of the rest of my lecture for today will be to show you how we can generate those types of field configurations, and also how we can map them in 2 dimensions and then also in 3 dimensions, and demonstrate that some field configurations such as the ones of Hopf vibration are indeed seen in an experimental system. All right, so the systems that we will work with, as I already mentioned, will be nematic and chiral nematic liquid crystal. Now, Jonathan in his talk already introduced to us topological defects, the 2-dimensional topological defects in particular, so-called disclinations or defect lines. In here, I again show you examples of such defect lines, right? So the 2-dimensional defect lines that we have in here are perpendicular to the screen. Those are the lines on which you cannot define orientation of liquid crystal molecules locally, right? And around the defect lines, we can characterize the local average orientation of those molecules by those director field lines that you already know a lot about. And so we can have defect lines with different strengths or different binding number. The ones that shown here have half integer strengths of binding number here and integer strengths binding numbers. So the S essentially tells us by how much director rotates around the defect line as you navigate it once, right? So in those cases, here and here, the director rotated by 180 degrees, plus 180 degrees or minus 180 degrees. And so if we divide it by 360, that's the angle by which we navigated the director field, we get the strengths 1/2 and minus 1/2 respectively. While for integer strengths defect lines, director field rotated by plus or minus 360 degrees respectively. And so we have 1D1 number plus 1 or minus 1. Right? So now, how would we see those type of defect lines in experiments? One way of seeing them is to use polarizing optical microscopy. Again, you already got a very good introduction to optical properties of liquid crystals. And so you know, as we place a liquid crystal sample between cross polarizers, then quite often if liquid crystal is not aligned in a very particular way by means such as rubbing of the surfaces, we will for free, without problems, get lots of defects in the sample, and the textures quite often for nematic liquid crystal would look like the one you can see in here on this picture, with defect lines that have different number of dark brushes emanating from the center. Again, the defect lines themselves are in here perpendicular to the screen, right? There are those points at which the dark brushes meet, and so so now what is important to understand in here is that the texture in such samples is typically two-dimensional, right? And so this is why we can use polarizing optical microscopy to reconstruct director field, right? Because as we would grow across the sample thickness, the director field does not vary too much, right, in those parts of the sample where we have dark regions, dark brushes, the director stays parallel to either polarizer or analyzer, right? And in the regions where we have bright parts of the sample, we have director at some angle with respect to polarizer or analyzer, but this director stays to be parallel roughly to the plane of the liquid crystal sample. Here's my question to you, which is based on what we just discussed, and I just want to make sure you don't sleep. You can actually follow what we discuss. So the question is, what do the dark brushes in such a texture correspond to? Okay, so we're getting some votes, but not, so it's just funny. There are more people with clickers, I know. Okay, I'll stop the system, make sure you voted. Alright, let's see what we got. So majority answered C, and that's a correct answer. Alright, so it was not unanimous, so please be more careful. Please follow what we discussed. Right, so C is correct answer, that the dark brushes correspond to regions where we have the director in plane of liquid crystal parallel to the substrates between which you confine liquid crystal sample, but oriented parallel to either polarizer or analyzer, right? And so now, but you could see that we could have defects with positive and negative winding numbers, right? So you might ask a question, how do we know what is the sign from experimental images, right? So in order to determine the sign of those defect lines, you could rotate the sample between cross polarizers. And so as you would be doing so, the defect lines that have the dark brushes rotating in the same direction as you rotate the sample would have positive sign, and the defects in which brushes rotate in the opposite direction can have negative sign, right? So to distinguish whether we have integer strengths defect lines, we can just count the brushes, right? Whenever we have 4 brushes, we know those correspond to integer strengths defect lines. Whenever we have 2 brushes, like in here, we know that those correspond to half integer defect lines. And then in order to determine the sign, we simply rotate the sample. And as I already mentioned, whenever the rotation direction coincides with the rotation of sample, positive sign. Whenever they're opposite, it's negative sign. So again, through those kind of polarizing optical microscopy experiments, we can learn a lot about the two-dimensional defects. And those two-dimensional defects, as I already told you, have a lot in common with cosmic strings, right? So using liquid crystal samples, studying phase transitions in liquid crystals, you can learn a lot not only about defect lines and their properties that are particular for these soft condensed matter systems, but maybe also you can probe dynamics and learn something that's related to properties of cosmic strings as well, because topologically they're similar. Now, however, we can also have defects with three-dimensional patterns of director fields. And those are point defects, the points on which the orientation of liquid crystal molecules is not defined, right? So the point defects can be located on surfaces or in the bulk of liquid crystals. When they are located on the surfaces, we call them Boojums, surface point defects. And the name Boojum was introduced by Mermin, famous physicist from Cornell University, who actually borrowed the name from the Lewis Carroll's character, The Hunting of the Snark, that you might be familiar with. So again, the surface point defects are point singularities on the surfaces of liquid crystals at which you cannot define orientation of molecules or liquid crystal director, in order to have such defects, you typically need relatively strong anchoring of liquid crystal at this interface. And so, in other words, liquid crystal should want to align parallel to this interface or at some angle in order to have a certain singularity of the types that you can see depicted in here. If the liquid crystal director wants to be perpendicular to the surface, or if it does not care at which orientation it's oriented to this interface, then we cannot have those types of point singularities at the interface of the Boojums. We can also have point defects in the bulk of liquid crystals, and it's useful to start introducing those point defects in the bulk of liquid crystals through the analogy with point defects in vector fields. So in here you can see the different types of point defects in vector fields. In order to characterize those defects, what we typically do is we encircle the point singularity by a certain spherical surface and then map the different orientations that you have on this encircling spherical surface to the sphere. So whenever we cover the surface of the sphere as to ones, we have topological charge of this defect 1. You can see that we can also have the case when we would cover it twice, then the charge is 2. The sign can be plus or minus 1 depending on the directionality of the vector field lines that approach this point defect in here. Now, when it comes to liquid crystals, it's important to remember that the director is non-polar in liquid crystals, right? So we cannot distinguish the two opposite orientations of the liquid crystal director, right? It has non-polar symmetry. And so because of this reason, the both radial and hyperbolic defects can be +1 or -1 at the same time. It depends on whether the convention on which direction of the vector field you assign to the director field line. So you can decorate the director field around the point singularity by vector field lines, and then depending on directionality you choose, this radial point defect can be +1 or -1. Likewise, the hyperbolic point defect in here can be +1 or -1, right? But if you have many point defects in your liquid crystal sample, and once you choose the directionality of decorating vector field, then the relative charges of all point defects in the sample will be determined after this, right? So that's important thing to remember. So again, now that we understand we can have not only two-dimensional textures, but three-dimensional textures around such point defects, it's important to know how do we characterize the director fields in three-dimensional textures with such point defects or other types of point defects and director structures. And so what I will talk next is how we can use nonlinear optical microscopy techniques such as multi-photon fluorescence and Raman scattering-based techniques to characterize director field configurations around point defects and also other field configurations. So what's important to understand in here that regular polarizing optical microscopy that we introduced before would not necessarily allow us to map the director field in 3 dimensions around such three-dimensional textures as you can see in here, right? Because light is propagating through the sample and does not provide us resolution that would be needed to know director orientation at each point around the point singularity in the experimental sample, having those types of defects. For this reason, we will need to resort to techniques that have three-dimensional optical resolution that allow us to visualize patterns of molecular orientation and director field orientation in samples. And so I'll discuss the techniques such as CARS and SRS. Those are Raman scattering-based techniques, coherent anti-Stokes Raman scattering microscopy and stimulated Raman scattering microscopy, as well as multi-photon fluorescence polarizing microscopy techniques. And also later on I'll show you how we can use laser tweezers in conjunction with those techniques so that we can not only image textures of director fields in liquid crystals, but also to manipulate them at the same time. And so we will see that those techniques allow us label-free, chemically specific imaging of field configurations in liquid crystal sample, and that we can simultaneously image and optically manipulate field configurations in those samples. As I already mentioned in the experimental approaches that I will discuss, we will use multi-photon excitation nonlinear optical processes, I hope many of you know how those excitation processes work. So when we have one photon excitation of molecules, we typically deal with just one photon that would allow us to excite molecule going from the ground state to some excited state. In the case of two photon excitation, we combine energies of two photons. In this case, can be also more than two photons, as we will see later. And then we still get emission, right, corresponding to going from the excited state back to the ground state. So the probability of excitation of this type in here is very low because we would need to have those two photons in the same location in space and time. And because of that reason, when we focus the laser light to excite a particular region in the sample, the probability of exciting photon, of exciting the molecule in the sample falls very quickly with falling of the intensity of light of the focused laser beam, and this provides us three-dimensional resolution so that we can do three-dimensional imaging of the samples without using any sort of confocal microscopes, right? So in here you can see the focusing of the excitation of molecules in a sample when we use two-photon excitation versus classical single-photon excitation. You can see that in the case of multi-photon, two-photon in this particular case excitation, we excite molecules only in the very center of the tightly focused laser beam, right? And the intensity of fluorescence is falling very quickly as we go away from this point of focus, right? And so this provides us resolution not only in the lateral plane perpendicular to the axis of the laser beam, but also along the axis, optical axis of the microscope and the focused laser beam. Right, so this is important because it will allow us to do three-dimensional imaging of the samples of interest. And so in order to be able to do this type of imaging or microscopy, we will be exciting the samples using red or infrared laser light. And as depicted in here, and we will be detecting the light in the visible part of spectrum where all detectors work quite well. Right? So this detection scheme is somewhat different from one-photon excitation, right? When we typically excite at a short wavelength and detect fluorescence light at a longer wavelength, right? When we use multi-photon techniques, two-photon excitation in particular, we excite the molecules with a longer wavelength laser light, but detect at shorter wavelengths. And this is quite useful because the penetration of many soft matter samples is much better when we use red or near infrared laser light, right? So you can excite samples quite thick samples, and you can go quite deep into the sample without big losses of excitation light. And then still you can detect fluorescence or Raman scattering in the visible part of the optical spectrum. Right, so what you can see in here is an experimental setup where we combine different types of nonlinear optical imaging with laser tweezers, right? So on the right side of the optical microscope is laser tweezer setup. Here on the left side we have nonlinear optical microscopy. And so the way it's realized is we use a femtosecond pacifier laser source that is then so it's tunable laser, but using photonic crystal fiber from single frequency input, we can obtain super continuum of femtosecond laser light, and then we can use liquid crystal spatial light modulator for spectral shaping, so that we can obtain different colors of pulsed laser light as input to excite the sample of interest and do different types of nonlinear optical imaging, right? So at the same time, on the right side, as I already mentioned, we have a continuous wave laser source in here that's used for manipulation of liquid crystals through the laser tweezers, and this is done by means of displaying different holograms on a spatial light modulator that allows us to obtain distributions, different distributions of laser light intensity in liquid crystal samples, so that with those you can manipulate defects or colloidal particles, as we will see later during my lectures, and at the same time you can also image them in 3D using nonlinear optical microscopy techniques that we will discuss. Right? So let us, now that we can realize all of those techniques at once in one single setup, and we can study topological defects and liquid crystal textures by means of nonlinear optical microscopy, by imaging them in 3 dimensions, and also by manipulating defects and structures in liquid crystals. Let us have a little bit closer view how those techniques work and what are the underlying physical principles on which they are based, right? So, as I already mentioned, we can use different types of nonlinear processes to visualize patterns of molecular orientation. And so when we look at the liquid crystal molecules like pentyl-cyanobiphonyl that you can see here, we realize it's essentially a di-molecule, right? Because if you were to excite it in the UV part of spectrum, like the wavelength of 327 nanometers, it would emit, it would fluoresce, right, in the spectral range around 400 to 450 nanometers. Because the absorption and emission transition dipole moments are parallel to the long axis of the molecule, we understand that the emission is highly polarization dependent, right? So it would depend on the orientation of polarization of excitation laser light that we would use. Now, instead of exciting those types of molecules in the UV part of spectrum, we could also excite them in red or infrared part of spectrum by using 2-photon or 3-photon absorption of those liquid crystal molecules, right? So if you double this wavelength, right, you get this wavelength in which you could also excite, right, by having laser light excitation at this wavelength. Or if you triple it, you understand that you could also excite at this wavelength, right? And those would be equivalent waves of exciting the liquid crystal molecules, right? We will still get emission in the same part of visible optical spectrum. You have a question?
Yeah, so it looks like there's a difference in energy between the emitted and absorbed photons. I was wondering where that goes. That's what it looks like here.
Right, so heating the sample pretty much. Right. Those are non-radiative processes. There are many of them, but all right. So as you can see, we can use not only single photon but also 2-photon, 3-photon processes to excite and get fluorescence from liquid crystal molecules like 5Cb molecule you see in here. We obviously don't want to do single photon process because that would require laser source in UV part of spectrum and very special optics, because all of you know that regular glass plates are not transparent in ultraviolet part of spectrum, right? And so that would mean you could not use regular objective lenses, you could not confine your liquid crystal sample between regular glass plates, right? And that would complicate things a lot. So instead of using UV excitation and single photon absorption processes, we use second order or third order nonlinear processes, and with that, in addition, we also get three-dimensional resolution, right, because of the nonlinear nature of those processes, right? And so now, because the absorption and the emission of the liquid crystal molecules is highly dependent on orientation of polarization of excitation light with respect to the orientation of those transition dipole moments, we also get orientational sensitivity. Right? So whenever they are parallel to each other, maximum light will be emitted from certain part of liquid crystal sample. Whenever they are mutual orthogonal, there will be pretty much no emission, right, of fluorescence when we excite this way. And whenever we have some intermediate orientations, when there is some angle between polarization of excitation light and the transition dipole in a certain of the 5Cb molecules or local orientation of liquid crystal director, we'll get some dependence on that angle, right? And so the nature of this dependence will depend on the type of nonlinear process that we use. Right? So the I in here is the order of nonlinear process. When we have second order nonlinear process of two-photon absorption, then I will be 2, right? And so we understand that in this case, when we excite the molecules through the means of two-photon absorption process, we'll have cosine to the fourth power of angle alpha type of dependence on the angle between polarization direction and the orientation of liquid crystal director. When we also use a polarizer in detection channel, which is collinear with polarization of excitation light, then it will be I plus 1 in here, so that would be cosine to the 6th power of the angle, right? Then if we go to the third order nonlinear process, so we use 3-photon absorption, it will be respectively 6 and 8th power, right? And so you can see that the emitted light intensity is highly dependent on the mutual orientation of polarization of excitation light and the local liquid crystal director, and therefore we can use this strong orientational sensitivity to map the three-dimensional director fields in liquid crystals. So first you can do it by means of probing fluorescence due to nonlinear 2-photon or 3-photon absorption. But next time, I understand I run out of time, right? We will also discuss how we can use stimulated Raman scattering processes to also map director fields around the point and line topological defects in 3-dimensional field configurations.
Thank you very much, Zach. Some questions for you now. We're going to run out of time, please. We have questions always, but I would perhaps ask them first. Yes.
I should like to mention that Boojums was also discussed in the context of the superconducting sleep.
Absolutely, yeah. That's where it was
It's a nice example for liquid crystal as well.
Yeah, definitely. I mean, the Merlin introduced originally not for liquid crystals. We borrowed that terminology.
Do the high intensities needed for these multi-photon processes actually also adversely affect other things in your sample?
That's a very good question. So the trick in here is to use short pulses, right, in such a way that although instantaneous intensity is very high, the average intensity is very low, so that you do not adversely affect liquid crystal samples. And actually, I have a quicker question later on for students related to this.
Okay. Any other questions at this point? Well, if not, there's one good one.
Is there any other advantage to using a 3-photon versus 2-photon process? I mean, in that last equation, it comes in there, so you have a higher discrimination, but you need much higher intensity. So
Yeah, but actually, so the intensity problem you can overcome by, just using shorter pulses. Average laser power is still, not a problem, but it gives you a better angular sensitivity, as you can see from this, and also a little bit better spatial resolution for the wavelengths of excitation because of the nonlinear nature of this process. So we mostly use 3-photon absorption. We do not go to 4-photon or so, even higher, just because that would require excitation further in infrared. But yeah.
Okay, it's lunchtime. We meet here again at 3:30 sharp. As you know,